Welcome and thanks for attending today's Ask CTE Contributors webinar event. I'm Dennis Faith, the owner and publisher of Cutting Tool Engineering. And I'll be serving as the moderator and host of this 1-hour webinar. So now it's time to go on to our webinar for today. It's focused on rough turning steel, as well as some of the relevant air quality issues that come with the territory. Again, I'm Dennis Faith, the owner and publisher of Cutting Tool Engineering. I've been that since 2018. I've worked here a lot longer than that. Next, I've got one of our first presenters. It's my honor to introduce. It's Martin Dillman, who serves as the Global Manager, Engineering/Applications for Greenleaf Corporation. Martin has worked in the machining industry for more than 25 years in a variety of roles. That began with work as a machinist/programmer in 1997. After earning an engineering degree, he moved into a process engineer role focused on high volume production for cutting and forming applications. Martin moved to Greenleaf in 2018 as an application engineer and has been involved in the research and development of tooling and inserts, as well as customer support. Our second presenter today will be RoboVent Senior Application Engineer Mike Meyer, who has more than 30 years experience in the design and installation of standard air and other complex industrial ventilation systems. He has designed more than 1,000 industrial ventilation and air pollution control systems. Mike also serves as an instructor for the Michigan Industrial Ventilation Conference, sponsored by the Michigan Occupational Safety and Health Administration. Before I turn things over to our presenters, I just want to remind everyone that today's webinar is an extension of a feature article published in this month's issue of Cutting Tool Engineering. The article, titled Making the Grade, discusses how the use of the right carbide inserts helps overcome any issues that might arise when rough turning steel. Greenleaf's Martin Dillman is among the contributors who were interviewed for the article. Accompanying the feature is a sidebar title, Air Quality Issues for Turning, which was authored by RoboVent's Mike Meyer. And with that, let's turn things over to Martin Dillman to get us going here.
All right. Well, thank you, Dennis. I appreciate the opportunity to join you today. Obviously, contributing to the article was a pleasure, but then being able to help present some of the information on Greenleaf's turning carbide grades is great opportunity to help others learn more of what we have to offer. So Greenleaf was founded in 1945 by Walter Greenleaf Sr. It's still today a family-owned and operated business with the third generation, Jim Greenleaf, as president of the company. You can see the facility in the picture here of our campus in Sagertown, Pennsylvania. It's in the northwest corner of Pennsylvania. We also have a small manufacturing facility in North Carolina as well. Greenleaf sells into over 70 countries worldwide with sales offices in Europe and China. No manufacturing is done outside of the US. We pride ourselves on being a made in the USA company and produce a wide variety of both standard and special tooling related to inserts and tool holders as well. Everything's manufactured. You can see the campus here with the multiple buildings. So everything from the raw material, the powders, the pressing of the inserts, the manufacturing of the steel tooling is all done on site. Walter Greenleaf Sr. was actually involved when he started the company in moving everyone from brazed carbide tooling to indexable tooling. So he was early on in that advent of changing the machining industry, moving it into what is traditionally used today. Every cutting tool company has lists similar to this one. You can see where the variety of grades that are offered based on the materials that they're suggested for. There are four main factors that are important for looking at when determining which carbide grade to use. Work material being the first one. Understanding what type of material you're going to be cutting, in addition to the hardness of the material, is very critical. Also, another factor that may come into it is whether the material will work harden. Certain materials do have that capability where it work hardens as it's being machined, which can make finishing operations very difficult. The type of operation that you're going to be running is also very important, whether it's a roughing application that would have heavy interruptions, cutting through scale, or for finishing applications, whether there's certain surface finishes that need to be maintained, how much stock needs to be removed during the finishing pass is critical as well. The machine work holding and setup, making sure you have as rigid a setup as possible. However, sometimes people will be working on equipment that's less rigid. Certain considerations that may need to be taken into factors of cutting tool pressures, things of that nature that may have to be considered. And then what is the objective of current operations? If you're looking at process improvements, whether you're looking to improve tool life, increase productivity with faster, stronger grades, or if it's a finishing operation, if looking to simply improve our surface finish, where certain more wear-resistant grades may come into play. The article was focused on steel turning, and one of the key things to note with steel turning is the many different types of steel that are available. There's a few of the groups shown here on this slide here. The carbon steels, you can see with the lower carbon contents, as well as alloy steels as well. All these materials have numbers which many people reference on a daily basis, all relate back to the AISI, the American Iron and Steel Institute classification system. These materials help designate what the alloying agents are in it, the material itself, and what the carbon content. The lower the number, the last two digits are, the lower the carbon content, which also can help indicate what the difficulty of machining may be. Standard material with a low carbon content, such as like 1010 carbon steel, low carbon content, very difficult to chip. It's much more ductile. So having considerations for that when selecting your chip form and grade are important. Alloying elements in some of the alloy steels, such as nickel, chromium, molybdenum, they'll add strength to the material, but can also create issues for tool life due to the heat generated in the cutting operations. Charts like this we use when considering hardness. You can see the hardness scale along the bottom axes there, and then surface speed referenced on the vertical axes. Whether the material is cutting with clean, smooth surface or in interruptions are also considerations. You can see the two color lines that we use here, the yellow and the green, just showing the green would be for interrupted, where you will want to reduce cutting speed slightly. And as you move from the lower hardness on the left to the higher hardness on the right, you can see the speed will drop. This is because of the heat that's generated when cutting. General rule, if you're cutting through interruption, roughing through scale, where you may run with a slightly slower pass in order to remove that rough exterior of the material until you get to clean, smooth cutting, where then you could elevate your speed, machine at a faster rate. When looking at the different grades and trying to determine what grade will work best, there's several different factors that can play into whether the grade is tougher or more wear resistant. Main ingredients in any carbide insert on the market is going to be tungsten carbide and cobalt. The amount, and the cobalt being the binder, the glue that holds the carbide grains together. The amount of cobalt binder in our inserts that we sell ranges between 4 to 10%, with the grain size and the amount of cobalt that is in there that plays into whether the grade may be tougher or more wear resistant. Typically, with a higher cobalt content, you're going to be dealing with larger carbide grains versus where you can reduce the amount of cobalt, so there's less cobalt that can be present in the matrix with a finer grain carbides. In addition to the carbide size, you could add other elemental carbides as well, with titanium carbide or tantalum carbide, which can help with the shock resistance or the heat resistance of the carbide grades as well. One thing I like to mention when we're talking about carbide grades is kind of comparing the carbide grades to sandpaper. When you think about for your coarse grit sandpaper, which is more for the roughing, you have that higher strength of the grains itself, can remove a lot of material, but the finer grains, more for your finishing applications, more wear resistant. Another factor when looking at carbide grades that's very important is the coatings. The coatings offer additional performance value for the grades. They'll provide a thermal barrier for the substrate, help provide lubricity for removing the material, letting the material move across the top of the insert, and reduce the chance for chip weld. Selecting the best coating is key for making sure you have optimum performance, but understanding all the mechanics in the process itself are important. Two major coatings here that we talk about is PVD and CVD. On this slide, you can see images of both coatings. PVD tends to be a much thinner coating. The coating itself has higher hot hardness. It's actually typical for PVDs, and I think it was mentioned in the article in Cutting Tool Engineering about when PVDs coatings are ran in a process, the heat that's generated helps activate the coating itself, causing it to actually get harder and protect the substrate even better. CVD coatings, much thicker, they're typically with multiple layers like shown here, offer more wear resistance and provide a better thermal barrier to the substrate below. You're not able to have as sharp of an edge typically with CVD coatings because they are much thicker than a PVD. So when looking at your materials that you're machining, it's important to understand what you're looking to accomplish. If you need to have that sharp edge for better shearing of material, you probably likely need to be with a PVD coating versus CVD. CVD works very well for roughing applications. And looking at chip forms, one of the major issues that you run into with cutting steel is controlling the chips that are created. Especially with more ductile materials, the chips can get stringy, have more difficult time controlling. So using the chip forms, and we have a variety shown here, different forms that are used, can help control that chip and lead to better part quality and tool life. Each chip form has an application range that it's designed for based on the overall form, the land size, the honed edge, the angles, and the chip gullet form itself, the little radius that's at the bottom of the chip form. All those play into how the chip is going to be formed. It's important to use the application ranges shown by any manufacturer to make sure that your operation's within those parameters. The depth of cut and feed rate are important in order to make sure that the chip is actually driven into the chip form and not pushed up over it. More ductile materials, you do need to have a sharper, more positive chip form versus shorter chipping material that can be controlled with a larger land. and lower angles. On this slide, we show the difference between running the same chip form at the same exact parameters, just varying our depth of cut. By not pushing the insert into the correct depth of cut as recommended, you'll see where the chip form dramatically changes. The top image with the 20 thousandths depth of cut, you can see this chips are much longer, stringier, can end up creating a mess within the operation, possibly even allowing those chips to get tangled around the workpiece, around the tooling, which can cause damage to the tool itself or shorten your tool life. The images with the 50 thousandths depth and the 125 thousandths depth, which are both fall within the ideal range recommended for the chip form, have much shorter chips. You're able to control those and have those evacuated with coolant and standard operating procedures for the machine. There's many types of wears that can be observed during steel cutting operations. Some of them can be very predictable, allow you to set up very repeatable processes. That's always been something key for me in my different roles, was trying to set up a process where we knew exactly how many parts we could achieve before having to index the insert or change the insert. Some certain types of wear, if not addressed, can end up causing catastrophic failure of the insert or potential quality issues for your workpiece. First type of wear I'm going to talk about is flank wear. This is our normal wear that we like to find as much as possible. You can control this. You know how many parts you're going to achieve per edge on an insert. You have a nice even wear pattern. You can adjust with a fair amount of knowledge to be able to increase speed. If you can't afford to shorten the total tool life of the tool, or reduce your speed slightly in order to be able to gain longer tool life, achieve more parts per edge. As far as prevention, there's nothing you really want to do on this. It's a matter of preference for tool life that you may want to change to a different grade. Chipping. This is commonly seen where you'll see along the edge notches along that edge. This is where small pieces of carbide actually end up getting pulled out, removed from that cutting edge. It can be acceptable to a certain point as long as you know when to expect it. If chipping is observed, it can increase in severity the longer you're in cuts. Those small chips where the carbides have pulled out allow for more heat to enter into the substrate, where it'll turn the cobalt into rubber and release even more carbides. This can end up causing random tool failure. Sometimes it can be confused with other type of wear issues as well if it's not caught early. One thing we recommend is evaluating in short intervals to be able to try and check to see if you're seeing this type of wear in order to try and determine how to best correct. If you can see for treatment of this type of wear, you'd be wanting to look at a tougher grade of carbide. Anything you can do to help reduce double cutting of chips as well, whether you may have to change into a different cutting chip form, or increasing your feed rate to thicken up the chip in order to have it evacuate quicker. Thermal cracking. These type of cracks are perpendicular along the cutting edge. It's caused many times in interrupted cuts. You'll see a dramatic change in the heat that's transferred into your carbide inserts in an interrupted cut through that heat cycling of going in and out of the material. If there's changes in the cut where it's being rapidly cooled along that edge, that's where you're going to end up seeing this type of thermal cracking. as the cracks form, this does allow for the material to actually get pushed into it during the high heat of a cutting operation. This is sometimes mistaken for chipping, so that's where running in shorter intervals, taking a chance to pull out the inserts, look at them, whether under a microscope or with a loupe, you can help determine what the type of wear is and what changes you may need to alter in your process. Plastic deformation, this is where you end up getting too much heat into the cutting edge itself. The carbide itself is, because of the heat, softening. You'll see where the entire form, and this picture is a little grainy. It was tough to get a great picture blown up on this, but the edge itself distorts. You start to see where the chip form may widen, or you'll see actual groove being formed because of the heat into your carbide inserts. This is more common in high temp alloys, although depending on the operation you're running in steel cutting, could happen as well. If you're running without coolant, this could also be present just because you are not getting that edge cooled throughout the cutting process. Changing to a more wear resistant grade can be very helpful in this. If you are seeing this type, it'll reduce the chance of the plastic deformation, but could lead to other issues of chipping depending on the type of operation you're running. The last type of wear I wanted to address was the build-up edge. This is common in more ductile materials, even into looking at stainless steels. You'll see where the materials are somewhat sticky, and if you don't have enough of a positive cutting edge, the material will start to build up. The top image shows a very dramatic amount of build-up edge on it. Looking at ways to either find a more positive chip form, a grade that can hold it edge strong is important as well. Want to make sure that if you are seeing this type of wear, it's just a matter of time before you'll end up getting into a chipping operation as well, because as that material builds up, new material can weld onto it, actually then pull off the coating and small carbides along the edge of your insert, which is going to shorten the tool life for your insert as well. Cutting speed is key for this type of failure or tool wear itself. Being able to run with more positive grade with higher speed, and probably looking at like a PVD coating for this type of operation as well. It will end badly if you continue to let it build up as shown in these images. Wanted to talk a little bit also about cutting through interruptions. We mentioned it as being present for the wear that you may see on carbide inserts. Some of the tips here you can see using tougher carbide grades, finding a grade that has the larger grains of carbide in there will help it hold up better. The cobalt that's mixed in actually provides a little bit of a shock absorption for the insert itself. Also using a chip form that would have a larger land. The land's going to be that flat surface towards the edge of your insert with even a heavier hone on that as well to help it hold up through the interrupted cuts, and making sure to maintain speed throughout the cut. A lot of times when you get into those interruptions, they have some extra vibration. The tendency is to try and slow down. However, you do want to try and maintain speed, the same speed throughout the cut as much as possible. Just a quick summary of what we talked about. Obviously, looking at the total operation, understanding the material, the hardness, and the conditions are key when selecting a carbide insert. Making sure you have a good review of the setup and operation. If there's considerations that need to be taken into the overall setup, making sure you have a good rigid work holding, and then understanding the wear that is found. It's always room for improvement for any operation. There's continuous development of grades. We are working on carbide grades constantly here, as is all the cutting tool companies, looking at ways to use the newer coatings that are out there, chip form developments based on these materials to try and optimize for the customers. And that wraps up my presentation for today.
Thanks, Martin. I'm going to switch the controls over to Mike.
Well, thank you, Dennis. And again, as Martin said, thanks for the opportunity to be able to talk to the audience. And again, also, thank you, Martin, for your presentation. Those operations that Martin was talking about, machining, turning, using coolants in removing metals from parts, generates particulates and aerosols that we need to control. So this presentation is talking about some of the risk associated with that, and then how do we deal with it. So Dennis did talk about my bio, so I'll skip that in this part of the presentation. And again, we talked about the risks that we will be talking about the risks associated with those turning and machining operations. So the agenda today that we're going to talk about is what are the risks associated with those turning operations and the coolant applied to those processes. How do you control those aerosol emissions? How do you filter it? How do you collect it? And then some considerations for system design. So let's get into the health effects of those turning and machining operations. These risks are known and actually well documented. It's respiratory irritation, ear, nose, throat, and skin irritations, odors, allergic reactions, neurological issues and damage, even cancers with some materials that are used for metalworking fluids. Hopefully all of us are familiar with the slip and fall hazards that these particulates, when they get on the floor, cause, and as a concern for our team members, we deal with that and prevent that from causing a safety hazard. And then possible combustion and flammability risks. Some of the materials that potentially can be used, especially with minimum quantity lubricant, MQLs, and even dry machining, could present some combustion and flammability risks. So what are those risks specifically as it relates to metalworking fluids with the human body? There's the hypersensitivity pneumonitis, lipoid pneumonia, occupational asthma, chronic bronchitis. Those are all issues that are a result of an immune system response that's triggered by those chemicals that are breathed into our lungs. Some are a result of long-term exposure, like chronic bronchitis. Some can be due to short-term exposure, like lipoid pneumonia. So regardless of whether an individual has been near those metalworking fluids for a short or a long period of time, there's potential health risk associated with that exposure. Bacterial infections and contact dermatitis. So when those fluids come in contact, whether it's the chemical in the metalworking fluid or a material that's growing, a microorganism growing in the metalworking fluid, there's a potential health risk there as well. So what severity, what degree of severity is that inhalation risk? What depends upon that? Well, first of all, it's the material composition, what's in the metalworking fluid, what makes up that metalworking fluid. And a good way to check that is look at the SDS, or what we used to call the MSDS. And the manufacturer is required to list the chemical composition of what that fluid is made of, and as well as the exposure risk. So looking at that SDS will help determine what the risks are. Particle size. The hotter the temperature of metalworking, the smaller the particulate. So if you're doing MQL or grinding or some very high-speed machining, that tends to generate more heat, and therefore the particle sizes that's generated in that mist will be smaller than, let's say, a lathe, and you're removing lots of material at one cut. Those particles tend to be a little bit larger. So smaller the particulate that's generated, that aerosols, the deeper they'll go into the lung. So particle size has a huge part in the risk associated with inhalating those materials. What else can cause it? It's the duration, frequency of exposure, and certainly pre-existing health conditions. Also, some of those processes will generate vapors, gas phase, so that comes into play with health effects as well. So how do you understand the exposure limits? Well, there's really three main bodies of published data that you can rely upon. The first one is just OSHA. In the OSHA 29 CFR 1910 subpart Z, that part of the OSHA occupational standards will list all of the exposure limits. They're called PEL TWAs, and that is simply short for the permissible exposure limit on a time-weighted average. And that is a legally binding limit. It's law, and it's enforceable by OSHA. And if you exceed the PELs and it's known, you'll get a visit from, an inspector, and you'll be required to do something about it. The other agencies, NIOSH, the National Institute for Occupational Safety and Health, and ACGIH, that's the American Conference of Governmental Industrial Hygienists. Those are non-binding recommendations, and typically ACGIH and NIOSH typically are more stringent, not always. Sometimes it's the same as the OSHA PELs, but typically they are more stringent. And also what we've seen through experience is that OSHA generally follows suit after some period of time of the ACGH recommendations, but not always. So some companies will use the OSHA as their internal EH&S standard, and other manufacturers I've seen use the ACGH standards as well. So when you look at that OSHA 29 CFR 1910, this is the kind of data that you'll see. You'll see that specifically for the topic that we're talking about today, oil mist generated from metalworking fluids in that process, the OSHA permissible exposure limit is 5 milligrams per cubic meter over a time-weighted average of 8 hours. So that is a pretty high limit of exposure, but that doesn't always tell the whole story. There could be other constituents in that mist that you need to be aware of. It could be in the material that you're working, an alloy, and there could be some materials in that alloy or other materials in the metalworking fluid that could also cause some concern, and you'll need to be aware of that and make sure that you're under the legal limit, OSHA PEL, or what your own internal guidelines are for protecting your employees. So understanding what those contaminants are, what chemical composition is in the metalworking fluid will help drive the solution, how well you capture it, how well you contain it at the source, the mist I'm talking about, how well you contain the mist in the machine, how well you capture it, how well you convey it, and then certainly filtering it so it doesn't get put back into the working environment or discharged to the outside environment. So how do we protect workers from these emissions? And probably the first question is, how do you know you even have a problem? How do you know you have an emissions problem? Without testing and having an inspector come in doing tests, or maybe your own internal testing, a good way is just looking at the air. And lights, the overhead lights, tell a really compelling story. If you look up at your lights and you see a haze or a halo around the lights, that's a pretty good indication there's particulates in the air. It may or may not be coming from the metalworking process. That's need to be sought out and determined by what processes are in the area. But typically, if you're seeing that haze or halo around the lights, those are very fine particles, typically submicron particulates in the air, and as the light refracts around those particulates, you're seeing that light refraction, and then haze. Another good sign is aerosols or particulates accumulating on surfaces, particulates inside control panels or inside areas that you typically don't housekeep. When you walk into many metalworking manufacturing areas, you'll have an odor that you'll smell. That's a good sign, and you may even be able to taste it. You just happen to taste it. And another sure sign is slippery floors. These materials, even though they may be submicron, will have a specific settling velocity. Typically, you don't see splashing out of the machine. It's just this material gets airborne and eventually it settles on horizontal surfaces, including the floors around the machine, and creates slip hazards. And we talked about the settling velocities. I use that term, and that's a good characteristic, the settling velocity of this hazy material that tends to get airborne. And these small particles that are generated during the metalworking process can become airborne. And here's what's happening. When the tool is interfacing the workpiece and you're flooding that work zone with a coolant, that heat at that interface vaporizes and actually vaporizes that coolant from a liquid into a gas, and that vaporization is very, very quick. It doesn't occur for very long, milliseconds, and then it cools. That vapor cools because of the air around it is ambient, and so it cools, and you're left with a liquid particle, but it's very, very small, submicron, 0.5 to 1 micron, something like that. And to give it a scale, the human eye can see about 40 microns and above. So we're talking about particles that the human eye cannot see. And typically what we're seeing, what we are really seeing with the haze, again, is just that light refracting around the particles. And so settling velocities, when these types of particulates get airborne, they stay airborne. Again, we're talking about 1 micron particle size. So if you look at that chart, a 1 micron particle will settle at about 5 inches per hour. So in still air, that particle will only drop about 5 inches per hour. So these materials that we're talking about tend to stay airborne. And as you're generating these particulates, the concentration just continues to go up until you either evacuate the zone with filtration or HVAC systems, or you capture it local to the machine and then filter it. So another question that we hear often is, why can't I just use PPE on those personnel in the specific area if there's an issue? And a phenomenon or a process that's very known to the industrial hygienist is hierarchy of controls. And so the last thing you should be doing is putting your team members in PPE. And there's things you should be doing before that. And engineering controls or capturing those particulates and filtering them should be done first. So PPE should be your last resort for protecting your team members. So how do you protect your team members? And a good way to look at it is from a 50,000 foot view is what I call the ventilation matrix. And it incorporates all the possibilities on how to ventilate the area and remove these types of airborne particulates from the process. And in the upper left-hand corner is what we call ambient filtration. It's simply putting a system in the facility and pulling in air from anywhere, not from the machine or the metalworking fluid process, but just ambient air in that space, filtering it and returning it to that same manufacturing space. Below that is the bottom left, source capture filtration. So it's connecting something directly to the process, whether you have a metalworking machine, the CNC machine that's fully enclosed, and you duct that cavity, that process to a filter out the contaminants and return that air, that cleaned filtered air to the manufacturing space, that source capture filtration. The other side is ambient exhaust up on the top right, and that's simply just connecting a fan or an exhaust system and capturing the air in the area, not at the source, and just blowing it outside. And the other bottom left is, bottom right, excuse me, is a hybrid of that. Instead of just capturing air from the manufacturing space, connect it right to the machine and do not filter it, but just blow that outside. The issue with ambient exhaust or source capture exhaust, not filtering it, is you're dumping that air outside. If you're in the northern part of the US or in the south where it gets hot, or in the north where it gets cold, typically then that may require some heating. You're pulling air in from typically somewhere else that's cold if you're ambient exhaust, or exhausting the air without filtering it and returning that filtered air to the plant. You're going to have increased HVAC or heating and ventilating cost as you pull that cold or hot air from the outside. So the preferred method is filtering the air, and that's kind of what this slide simply presents, and that is on the dilution or exhausting the air to the outside, you're dumping dirty air or unfiltered air to the outside, and you're bringing fresh air in. But typically, if it's, again, those extreme temperatures, you'll have to temper that air one way or the other. Air filtration systems is by far and away the best. It's the best in class. You can filter the air and return that air to the building. It does not upset your HVAC, heating, or cooling balance on your facility, and you are returning the clean air to the plant. You don't have to worry about permits to operate or permits to install as you dump unfiltered air to the outside environment, outside of your facility envelope. So, looking at these processes that generate aerosols from turning and machining, again, the best way to do it is employing a well-designed, well-constructed, and well-maintained air quality system, filtering that air. Most machines today, turning and machining processes, are fully enclosed to contain that metalworking fluid, and that presents a very opportune situation where you can exhaust just that enclosure and filter it. You don't have to come up with any custom hood and a part of the system that will impede productivity. Most machines that are fully enclosed are fantastic opportunities for filtering the air and returning that air to the plant and creating a nice balance for your facility from airflow. So again, we talked real briefly about types of particulates. Typically, when you look at a Sylvan chart, a chart that talks about or shows filtration particle sizes, aerosols from machining operations tend to be submicron up to about 10 microns. So these are very small particulates. They present problems such as they're wet, they're liquid, they're sticky sometimes because they're going to contain some of the metal, the base metal that you're working. They may also contain some atmospheric dusts. Surface tension will capture those atmospheric dusts. So what presents to the filter may not just be a nice, clean metalworking fluid. There's going to be some other contaminants involved. So you'll need to be concerned about those as well. So considerations in particulate control system design. How do we design these systems? And the strategy really depends upon what types of materials you're using in the metalworking fluid. Is it oil, synthetic? Is it water-based? Each one of those presents different challenges to the filter. And is it a manual process or is it a robotic process? In other words, what is the exposure to the human? So again, the goal, the overarching goal, is to capture and remove these particulates from the breathing zone and controlling the exposure to our team members, and also preventing it from exhausting into the facility and affecting people outside of that metalworking process. System design considerations. When we design the actual mist control system, we talked briefly about particle characteristics, what's in that chemistry, what's in the metalworking fluid, emulsifiers, anti-rust or corrosion properties or chemicals. All those things will have some bearing on the filter selection. What type of control device? Is it a dry collector or wet collector, depending upon what types of particulates we're going to be capturing? duct design. There's two schools of thought on duct design, and that is maintaining a high enough velocity to convey that particulate from the process to the collector. And there's another school of thought that says run that ductwork velocity at a slow enough velocity where it's going to condense in the walls of the ductwork and potentially flow back to your process to reclaim that fluid, or perhaps pitch the ductwork so it collects back into the control device, the collector, and deal with it that way through a drain or some other methodology. So types of particulates, we'll wrap up here fairly quickly. Types of particulate collectors, and the heart, or really the base of the collector, is what type of filter you're using. If it's a dry process or MQL, you may want to go to a cartridge style filter that's meant for dry filtration. If it's a wet process, a filter that's meant for liquids, and there's a wide variety of those types of filters. There's filters that are near HEPA quality, 99% plus for submicron particles, and they tend to last a very long time if you deal with the non-solubles ahead of it. And then to the other extreme are lofted fiberglass throwaway filters that tend to last a few weeks, maybe a few months. So there's this extreme in efficiency and also longevity of the filters. If you're dealing with odors, that is constituents in the gas phase, a filter will not capture those odors. So you'll need to use what we call molecular filtration. It's basically activated carbon, activated charcoal that is able to absorb those gas phase emissions and get rid of the odor from the process. So that's always a possibility. A mist collector is typically a device that filters liquid aerosols from the air, separating that liquid aerosol from the airstream, collecting it. If there are solids present or non-soluble particulates, usually from the base material that you're machining, such as grinding. Grinding will have typically lots of solids in the airstream that you're collecting, or maybe some other biocides that you have, or some other chemistry inside the metalworking fluid, and certainly water-based fluids where that water will eventually evaporate and leave almost a gummy material in the filter. So those are some of the nuances associated with collecting these metalworking fluids. And again, it just really begins with determining what type of metalworking fluid you have. If you have dry particulate, there's a simple picture of a dry filter that can be used for MQL or for dry machining, small footprint, high volume, really high efficiency. Again, almost HEPA, but not quite HEPA quality air. So one of the last slides we'll talk about is how do you capture the particulates? And there's three types of hoods. One is an enclosing hood, so basically using your machine as an enclosure to keep it from escaping into the environment. You're containing that contaminant, and then you just evacuate that cavity, that machine cavity, to a filter system. And that is by far and away the preferred method for industrial hygienists and for myself as well, from a ventilation engineer. That's the best way. It keeps it from escaping into the environment. Another is the next type is a receiving hood, and that is using the momentum of the particulate generation. And the way to think of it, I guess, would be looking at it like a catcher's mitt. So if you have a grinding operation, for instance, and there's not an enclosure around it, that grinding wheel is going to throw the particulate. The lathe is going to throw the particulate in one unique pattern. Well, use that pattern as the location of your capture hood, your receiving hood, and then duct it to your filter. And the final hood type is a close capture hood, putting a hood close enough to the source with enough momentum from the air, enough capture velocity to capture those particulates and convey it to where you want it to go, which would be to the collector. So the last slide is really affecting what are those factors affecting air quality in the manufacturing space. Number of processes generating those emissions. One machine will not generate as many particulates, these aerosols, as 100 machines. The generation rates or the productivity of those machines will have a huge play in it. Size of the manufacturing space. The larger the space, the more it has the ability to concentrate dust before it reaches the PEL. Air makeup systems, supply systems, exhaust fans, spot cooling systems, all of these other air infiltration, exfiltration systems will have an effect on the overall performance of a mist control system, but also on the overall air quality within your facility. Effectiveness of current systems. If you have current filtration systems, how effective they are. Some systems are not fairly efficient, so you'll have particulates coming out the backside. You may not be able to see them because, again, they're submicron, but you could have variation in your air quality based upon that performance of existing air quality systems, and the chemical makeup of metalworking fluids and particle size of contaminants. So finally, use the OSHA PEL TWAs or better to protect your team members. Make sure you're complying with those OSHA standards as well as NFPA. And there's a fantastic resource from ACGIH. It's called the Industrial Ventilation Manual. It is the go-to resource for designing ventilation systems, whether it's for a dry particulate, a wet particulate. If anyone has any needs for that ventilation manual and you have trouble locating it, please get with me and I'll help you do that. If you have a lack of resources or lack of time, let's say, within in-house for designing systems, ventilation systems, find a qualified firm or supplier, and they'll certainly be able to help you design those systems. So that's all I have. Thank you, Dennis.
Thank you, Mike. So we have a little bit of time left. Appreciate both Martin and Mike for your presentations. Right now, we're just going to start with some questions that came in that were questions that submitted by those of you when you registered. You took the time to submit a question that you wanted to have addressed. First of those is really directed for Martin. What are best practices for achieving good surface finish and acceptable tool life on an interrupted cut?
That's a good question. The one thing to consider with interrupted cuts, and I touched on a little bit in the presentation, is having a strong enough edge. So making sure the chip form is capable of holding up through the interruption, but also with a grade that is wear resistant enough to be able to hold up for the entire length of cut to provide the surface finish you're looking for.
Okay. Now there's a question for Mike. You probably covered this, but how do I know if I need a filtration system for my machines?
Well, I would say if you have a metalworking process and it's highly likely you're going to need a filtration system for that machine. But to just know, how do you know after the fact that you've been running for a while? It's that haze up in the lights. It might be employee complaints. And the one thing that we're seeing, especially with a tightening labor market that we've seen for the past few years, the firms, and this is our experience speaking, by the way, the firms that we're seeing that are attracting the best employees are those firms that are creating a really good working environment. And so, so how do you, again, I would say that if you've got a haze or you've got employee complaints, or you need to, attract good employees, you most likely need a highly effective, efficient filtration system.
Mike, for you, should I wait to install the ventilation system after my turning machines are set and operating, or afterward?
Well, that's a good question. That's a really good question. Typically what we see is it's done after the fact. Again, speaking from experience, most staff at the facility will get the machine set, and the filtration is usually an afterthought. But most manufacturers have enough data available to allow someone like myself to design that ventilation system up front. It really revolves around three components. The first one is the size of the machine, the volume of the cavity when the doors are closed and the machine is doing its thing. What is an open volume that, you know, in cubic feet, that tells us, or gives us a really good indication of how much airflow you'll need. Also, when the doors are open, how fast do the doors open to get access to the part when it's finished or changed tooling or whatever after the cycle time. That door opening is important as well. And then what metalworking fluid that you intend to use. Those three components go into the design basis for it, so you don't have to wait until it's installed. Manufacturers of those machines will provide us enough data to design a really efficient system. But a good question. Thank you, Dennis.
Oh, yeah, and we're running out of time here, unfortunately. But what is the best filter for use on a wet machining process for air quality?
Another good question. I kind of mentioned it very briefly, and that was what we call a coalescing filter. There's this continuum from the best in class of coalescing media to the other end of the spectrum, and that's some kind of a fiberglass, typically lofted. Once that lofted fiberglass becomes saturated, when a mist droplet hits it, another droplet comes off the backside, so its efficiency greatly degrades once it becomes saturated. A coalescing filter, nearly HEPA quality, not quite, but nearly, it loves lots of liquid. So once it becomes saturated, now it starts to drain that coolant from the fibers and stays as efficient as it was when it was brand new. And I've seen filters. I actually put a system in at a manufacturing facility in Tennessee, a large automotive manufacturing facility in Tennessee, where the filters lasted 20 years. Obviously, those are more expensive, and that would make sense. Those types of filters are more expensive, but you know, I guess the short answer depends on what your goals are. Little maintenance and less ongoing cost, that would lead you to the coalescing type media, or upfront capital cost and less regard for ongoing maintenance. It would be the lofted fiberglass filters.
Thank you, Mike. With that, you know, I want to just thank everyone. Our presenters, Martin Dillman from Greenleaf Corporation and Mike Meyer from RoboVent. Big thanks to our audience for attending today's webinar. It's not easy to take the time out of your day. I really appreciate that. And please feel free to reach out to either of our presenters via email should you have any further questions, and their information is right there on the screen. In addition, I just want to point out that if you want, there are handouts that are available through your control panel, and you can download those straight to your computer. In addition, once this entire presentation is available via recording, which should be sometime before the end of today, you'll also have access to the PDF handouts through our website at ctemag.com. And you'll see in the webinar section of our website where you can locate a recorded version of today's webinar. With that, Martin, do you have any closing comments or anything else you'd like to add before we close out?
No, nothing else for me. I appreciate the opportunity, Dennis, and appreciate everybody else taking time to join here for this afternoon's presentation.
Thanks. Mike, how about you?
Ditto for me. Thanks for all the attendees who took time out of their day.
All right, and with that, that's the conclusion of today's webinar, and we appreciate your attending, and please take a moment to complete the feedback survey that you'll see as soon as I close out the webinar. Thanks again. Have a great day.